Alright, Barrons Fundamental Engineering Exam Book 2008, continuing chapter continuing chapter 3.9 Chemical Kinetics. Basic concept: chemical kinetics is a state with the rates of mechanism of chemical reaction. Reaction is a kinetic property, depends on the mechanism and contrast thermodynamic property discussed in section 310. Independent mechanism thermodynamics can tell whether or not a reaction is spontaneous, but kinetics tells us how fast the reaction occurs and happens to fast enough by any of the interest value of the most common way to measure a rate of reaction disappearance of reactant. This is change of the concentration reactant within time. Reactant rate equals negative resultant change in concentration over time times minus negative concentration reactant 2 minus concentration reactant 1 over time 2 over time 1, where C is the change of the concentration reactants and T is the elapsed time. Subscript 1 and 2 refer to concentration corresponding times. Respective reactant concentration decreases time making constant concentration 2 minus concentration 1 negative quantity minus signs u to the positive quantity. Reaction rate is calculated just as well as changing of the concentration time product as resultant concentration over the resultant time is positive quantity. It's important to remember the reaction rate is constantly changing of the concentration over the time represents an average rate. Instantaneous rate is given as the first derivative is derivative concentration over derivative time. Reaction rates and laws of the constants. For general, AA plus BB equals GG plus HA. Rate of law of equation expressed as rate is in rate of constant times AX times B to Y. And reciprocal times A and B represent molar concentration reactants at A and B. X and Y are exponents denoting the order of reaction from the reactant species. X and Y must be determined experimentally. Sum of the exponents X plus Y is called the overall order in the reaction. In Present's case, it said the reaction is X order A, Y order B, and X plus XY order overall. Consider the example following rates. Nitrogen oxide plus carbon oxide, carbon oxygen. Experimental determine the rate of law of the reaction. Rate equals rate of constant times sodium oxide square. This means with the rate of second order and zenith order. CO is the second overall order. Consider another example of decomposition. Dinitrate pentooxygen. Dinitrogen pentone oxygen. Experimental determine the rate of law of this reaction. Rate is constant of the dinitrogen pentoxide. The rate of decomposition first order is the nitrogen pentoxide rate constant. Experimental measured at constant 5.2 times 10 to the third at 65 degrees Celsius. First and second order reactions for action known to be first order in particular series. The dinitrogen pentaoxide decomposition discussed above rate is written. Rate is determinant A, negative determinant A over the determinant time is equal to the resultant A over the resultant time equal to the constant A. First order reaction means with the doubling of the concentration, A doubles the reaction rate with the equation integrated given more usable result. Alright, the IN A 0 over A equals constant over the temp and time. Resultant time is written as first order reactant A. First order reactant A is minus for the constant and resultant time. Similar fashion, integrated rate equation for second order reaction 1 over A over equals 1 over AO times K plus negative 2 half-life reaction. Quantity defined in half-life reaction can be also determined. The half-life is the time required for the concentration reactant half the initial value. First order result reactant half-life independent initial concentration is given. Time 1 2 over 0.693 constant, and then it goes for second order reaction half-life depends on initial concentration is given as time over 1.5 times 1 over the constant over the second order reaction. Depends with the temperature Arrhenius equation. Arrhenius models rates for the reaction assumed that the molecules undergo collisions before they react. The number of collisions per unit time. A frequency factor model assumes that not all collisions result or lead into a reaction. Rather, only those with sufficient energy, called the activation energy, and allowed molecules to reach activated complex will each result. The rate of constant x is function of the temperature can be expressed theoretically in Arrhenius equation. Constant x function of the temperature of the Arrhenius equation. Fact A equals factor measure number of collision per second times E to the activation energy in joules calorie over universal gas constant unit consistent of activation energy joules and calories per mole times the absolute temperature in Kelvins. A most useful form of the equation can be written as constant function temperature is in initial order A over activation energy joules per mole over the universal gas constant consistent with joules calorie and time absolute Kelvin. Rate of constant 1 and constant 2 differ in temperatures. Temperature 1 and 2 are related. Initial order of constant 1 over constant 2 is equal to activation joules in calorie over universal gas 1 over T minus 1 over T2, 1 over T2 minus 1 over T1. Alright, catalyst. Substance with the increased rate of the reaction with themselves with the consuming of the reaction are called catalysts. They work lower activation energy. The barrier required for the reaction perceived with the catalyst may be in the same physical state with the other species of the reaction. Homogeneous catalyst. Different physical states, heterogeneous catalysts. Chemical thermodynamic thermochemistry. Basic concept of thermodynamics is the study of the transformation. Thermochemistry is the study of the thermal energy and the change of the accompanied with the chemical and physical change of the energy transferred between the object system measured with the temperature of the changes. Energy's property of the substance system and cannot be measured directly. Process occurring with the system produces releases heat with the surroundings is called the exothermic and is valued with a negative sign with the convention process absorb the heat from the surrounding of the system endothermic value. In its value, positive sign. Note that the exothermic reaction is not necessarily spontaneous reaction. Negative sign should not be interpreted as such. The type of the interpretation criteria for the served as resultant or the Gibbs-free energy is discussed in page 115. Enthalpy and Hell's law. Since chemical reactions involve the forming bonds, energy changes generally accompanying reactions initiated with the reaction activation energy, but the must first supply with the reactants to each activated complex, whether or not the reaction is spontaneous reaction change with the enthalpy, which is heat content known as heat of the reaction, is associated with the process of the amount of the heat exchange liberated with absorbed surrounding under the constant external pressure and managed by the experimental, directly calculated, theoretically, indirectly expressed either in kilojoules, kilocalories. Enthalpy change with the change with the heat with the deviation with the defined with the heat with the reactant product is derived with the element subscript of the meeting of the measure of the under normal conditions of the NTP as opposed to STP. As regards of the reaction, Hess law state with the enthalpy change with the chemical reaction, same with regards to the number of separate reactions. Reactions interest some of several other reactions. Individual heats reactions must be algebraic in order. So we have the heat of reaction is equal to the logarithm of heat of the products minus the heat logarithm of the the resultant heat reactants. First law of conservation energy. Understanding the laws of thermodynamics usually define and distinguishes surrounding very carefully in generally three systems: cloud system, a system that no matter enters in or leaves; isolated system, a system that no mass heat enters or leaves; open system, a system where mass heat can enter and leave. Furthermore, there are two kinds of boundary walls or process diathermal walls, permanent transfer of the heat between system and surroundings. Orbitic walls, walls that do not permit transfer of heat between system and surroundings. Good insulated. First law of thermodynamics could be in several ways. For example, energy universe constant, total possible energy changing equal to the sum of the energy change system plus the energy change surroundings. During chemical physical change, divine system energy that can neither be created nor destroyed but only change form. Expressed in mathematical terms as Total internal energy change of the system is equal to the heat absorbed by the system from the surroundings minus the work done by the system of the surroundings. For adiabatic processes, the quotient is equal to 0, so the resultant energy is equal to the negative work done on the surroundings. For isothermal changes, ideal gas, the resultant energy is equal to 0, since E is the energy function is temperature only. The pressure volume work of the ideal gas expression and compassion work done on the system is equal to the relative pressure times the differential volume. Pressure results in volume if the pressure is constant, and volume differential pressure of the differential volume is equal to the differential of the number of the rate, or rate times time over the volume times the differential over the rate. So the resultant energy and resultant heat are related to the equation. Resultant heat is equal to the resultant energy times the pole pressure times the resultant volume at the constant pressure. Other types of thermodynamic work may include electrical work or magnetic work. Or the second law of entropy. The second law of the thermodynamics could be expressed in several ways. For entropy, S, that is the randomness disorder universe, either stays the same or increases but never decreases. During the physical chain chemical reaction, total entropy change is resultant S of the system plus surroundings, either 0 or the positive, negative, never negative. It may be calculated reversible heat quotient, either absorbed or liberated system divided by the absolute temperature. Resultant entropy change is equal to the quotient over time. Construction per metrical motion machine is impossible. It's impossible to build a heat engine with 100% efficiency. Corollarily, second law has referred to the zeroth law, stated that heat always flows with the regions of the hot and regions and cold spontaneous entropy. Also measures statistic disorder randomness system are all real natural changes which are spontaneously reversible. The entropy system increase with the entropy change. The entropy change is positive idealized change with a reversible infinite slow. The entropy change is equal to 0. Mathematically, they must be expressed as entropy change is equal to system plus system entropies and plus system entropy surroundings equal to entropy in the universe greater than or equal to 0. Phase transition entropy change of transition is equal to quotient transition over time equal to resultant heat transitions, where resultant heat transitions may be heat vapor or heat fusion. For heating any substance without vapor, the transition heat gain or loss is Q may be expressed. Heat loss or gain equal to the mass of the substance in the gram, the moles times the specific heat and capacity in suitable units, resulting in the change in temperature in the degrees in Celsius and Kelvin. For other processes involving change of the temperature of solvent, the entropy change is equal to the specific heat and volume, and suitable it be the in order time 2 over 1 minus the number of the rate in order of volume 2 and volume 1. Alright, third law, absolute zero. The third law of thermodynamics states that it is impossible to reach absolute zero. Finite number of steps. Another version states that absolute entropy is a perfect crystal and zero, absolute zero, since every form atom is perfectly in place and has no kinetic energy. Gibbs free energy spontaneity of reaction. Gibbs free energy rates. Gibbs free energy is defined as free energy resulting heat from temp time of the entropy change. And chief value of the unequivocal measure of the indication reaction spontaneity includes both the enthalpy terms of the heat and entropy terms of change. Every reaction simultaneously reaches state of minimum energy, state of maximum entropy. The sign of the Gibbs free energy is negative reactions produces simultaneously as written positive. The reverse reaction proceeds spontaneously. For equilibrium, the Gibbs free energy change expresses Gibbs free energy is equal to negative rate times time. Initial order of constant expression in general. Gibson free energy is equal to the negative rate times time constant gaseous phase pressure and for gaseous phase reactions. Alright, 311 electrochemistry, basic concept, one category chemical reaction basically discussed and described in section 3.4, oxidation reduction reactions. Redox reactions for short, recall for following criteria: oxidation, loss of electrons, gain of oxygen, atoms, loss of hydrogens, reduction, gain of oxygen, loss of hydrogen, gain of hydrogen. Two different metals are placed in physical contact with respect to the ionic solutions are the connected with a suitable conductor separated with a salt bridge, forming a closed circuit. Potential difference voltage current flow observed. Figure 3.2, page 116, with the arrangement of is known as electrochemical cell. Underlying electrochemical reaction involves spontaneously oxidation reduction. Electrochemical cells are basic operation of all batteries. Reaction current flow for the spontaneous, as in battery. The cell is called the voltaic or galvanic cell. Instead of electronic energy must be supplied. The cell is called electrolytic cell. Is the process known as electrolysis. Electrochemical cell is composed of two half cells, and one called the anode, and oxidation occurs. In others, is cathode reduction occurs with each reaction as a half reaction. The sum of the two half reactions, the overall of the net reaction, resulting in iron or corrosion over the metal involved with the oxidation reduction process with a net electrolytic potential unit is a measurement commonly used with electrochemistry involved with volt, electron, volt, and coulomb and amp. Alright, Nernst equation allows describing the relation between the concentration of ionic solution voltage produced in the net reaction called the Nernst equation, expressed as E net. The Nernst equation is equal to R rate times sign over the F, number of moles of electron transfer per unit reaction. In order of the ratio molar concentration products and molar concentration reactants of the aqueous and gaseous species, the solutions, solids, or liquid species as secluded. For condition, the temperature is 25 degrees Celsius, 298 Kelvin, or quotient 23036 log quotient. Nernst equation simplified. E net of E at 0.059 over the number of moles electron times the log of the quotient. Single 1 volt, 1 joule per coulomb, 1 amp, 1 coulomb per second current in ampere times the second total charge transferred in coulombs. Also, potential in volts, charge in coulombs equals total energy produced used in joules. Table exists present reduction reaction metals along with the selected nonmetals, their corresponding potentials relative to the stream of the hydroelectric. With those reduction potentials is taken zero. More extensive tables and decay. Potential to oxidize organized separately according to the acidic alkaline conditions. Important note of the reduction reaction potential that depends on the pH solution as well as the present complex agents. The listing often referred to electromotive series. The reduction potential is given in the Nernst equation values of the volt and Nernst coefficient values listed in positive reaction spontaneous is written. Negative reverse reaction is spontaneous subscript 0. It refers to the standard condition temperature at 25 degrees Celsius, concentration 1.00 moles for any ionic solution, particular pressure of 1.00 atmosphere and gas present. The listing referred to activity series of metals of the terms that indicate the metal more likely to relative to another relief the electrons oxide react. For example, the metal lithium, the highest negative of the Nernst equation value is negative 3.045 volt, while magnesium Nernst equation value is negative 0.26363 volt. Therefore, element lithium will be oxide react more easily with the element magnesium. The non-metal fluorine has the highest pressure of the Nernst equation value plus positive 2.87 valves. Is easiest to reduce most electronic negative element. In other words, the larger negative Nernst equation value means the reactant is good producing agent, and larger positive Nernst value indicates a good oxidizing agent. Table 3.5 lists and standard reduction potentials at 25 degrees Celsius, normal half-life cell reactions. Consider copper zinc electromagnetic cell in figure 3.2. In right half cell cathode copper 2 inicon solution reducing copper to 0, indicating copper metal solid. Left half cell anode zinc 0 as being oxidized zinc 2 that dissolved in solution. Anion sulfide tetraoxide negative 2 are separate ions, do not participate in reaction. Salt bridge necessary to maintain electronic neutrality. Retard shorthand notation of cell and files. This is understood that the anode shell of the oxidation curve written first separately with the double the vertical line cathodic shell reduction occurs simple vertical line separated with a solid electrode from aqueous solution, which it was displayed for the concentration of solid is expressed in the parentheses. Two half reactions followed with an algebraic sum reaction with the written as. Note that the electronic exactly cancels each other out. Two half reactions do not appear in the net reaction. If this does not happen automatically, one or both of the half reactions must be multiplied by a suitable coefficient integer coefficients energy to obtain exact cancellation electrons known as also. Positive value understood with the nitron's value indicates this reaction proceeds spontaneously and produce 1.1 volts under standard conditions. Use of quantitative relationship: 1 mole of electrons is equal to 96,485 coulombs. Change of current C current equals current over second times time second. 1 ampere is 1 coulomb over 1 second. 1 volt is equal to 1 joule over the 1 coulomb. Faraday constant is equal to 96.485 coulombs mole. Electron gas constant is R to the 8.31 joules Kelvin times mole. Numbered moles of the the electron is negative electron is equal to the current times the time times the Farad constant. Alright, 312, organic chemistry. Organic chemistry is the carbon. The compound is of the chemistry of carbon and its compounds. Carbon's ability to bond itself with other elements, including hydrogen oxide, nitrogen, sulfur, fluorine, chlorine, bromide, iodine. Numbered or cataloged organic compounds, natural plus synthetic, is in the millions rapidly with expanding the selection rules of structure. Simple organic compounds, associated rules, non-molecular outlined. Hydrocarbons are the simplest class of the organic compounds contained with the only carbon hydrogen class names of the base for the naming. The more complex organic compounds, carbon normally makes 4 covalent bonds. Compounds which are also possible carbon bonds containing hydrogen called alkaline saturated hydrocarbons. Unsaturated hydrocarbons, 1 or more carbon to carbon double bonds. Triple bonds are aromatic benzyne base bonds, generally understood unsaturated hydrocarbons, more reactive saturating reducing agents than their saturated counterparts. Soluble alkalines related with the nonpolar nature of the molecules. Alkalines with insoluble water molecules are polar bonded with one another under hydrogen bonds. Alkaline molecules are nonpolar, are bonded with weaker intermolecular dispersion forces, London forces, Van der Waals forces. Therefore, alkaline molecules are not readily attracted to water molecules and cannot be part of the water structure and irregular, but certainly hexagonal network. The fact demonstrates the general solubility principle dissolves because most alkalines have a density less than the density of water. The compounds usually float to the top. Structure of the normal and straight chain alkaline is shown below. The chemical formula for the alkalines is carbon NH2N2 plus 2. Shows methane, ethane, and a general alkaline structure. 3-4 lists formulas properties for the figure 10 hydrocarbons known as homologous series, also with the carbon 20 and carbon 30 hydrocarbons. Alkaline can also be branch chain hydrocarbons, which can be from numerous isomers. Isomers are substances with the same chemical but different structure form, given the rise of two different chemical and physical properties, determine whether the two compounds isomer each other. Count with the number of the carbon atoms, hydrogen atoms, any other type of the atom that present is each compound. If the numbers are each type of amount of the two compounds are equal to the compound's isomer of the carbon 20 hydrocarbon. Ecosane, for example, has 366,000 isomers. Analogous series consists of hydrocarbons, 1 double bonded with the alkanes, and how the general formula carbon N times H2N. Hydrocarbons with 1 triple bond are called alkalines, have the general formula of carbon N H2 negative N. Ethanol, acetylene ethanol, or ethane carbon hydrate. More organic compounds, common names assigned with them before the formal system nomenclature called the IUPAC system, developed with the 1960 following rules now apply with the name of the organic compounds. Select the longest continuous change of carbons, number of the carbon atoms in the chain, beginning with the end of the nearest branch, assigned with the name of the position number, the indicate with the branch substituent, and for the functional groups include with the ene, with the double of pound, with the wine, triple, with the one of the same substitute, with a period, with the Greek prefix, di, tri, tetra, etc. Table 3, 6, page 125, with the names of specific function groups numbered with the longest continuous change and with the weight substitute with have less possible numbers, and it goes example. Cyclic hydrocarbons begin with a propane C3H8. Cyclic structure hydrocarbons possible hints for the cyclopropane cyclobutane, and so is also shown in the table 3.8. Ranged hydrocarbons generally are more reactive because of the ring tension of their straight and branch chain counterparts. Aromatic hydrocarbons. Compounds containing benzene ring C68686 classified aromatic benzene ring shown in figure 3.3. System alternating single to double bonds. Benzene, an interesting property. Even when three double bonds, benzene undergoes no additional but rather substitution because it's relatively unreactive. It forms compounds toluene and monochloride, dichloride, and trichloride benzene. These six carbon bonds are equal in hybrids and single to double bonds. They are longer normal double bonds but shorter single bonds. These type of ring systems exhibit resonance which give the characteristics to stability. For nomenclature purposes, each of these carbon atoms benzene ring is assigned with a number of 1 through 6 clockwise fashion. Common aromatic compounds, benzene derivatives with the common names of the IUPAC names shown in figure 3.3. Subsequent groups added in 2 at a time. The positions occupy a ring may be 1 to 2. One to two, known as ortho or zero. 1 to 3, also known as meta. M or 1 to 4, also known as para. Alright, function groups. Hydrogen atoms replaced with a certain amount of the atom function groups are formed. The function groups give it a discrete chemical physical property. The name of the function groups along the structure listed in table 3.6. Alright, 3.13 summary. In conclusion, the study of the chemistry useful several ways to help with predicting the chemical reaction can be spontaneously occurred between two or more substance chemical thermodynamics, whether the products of the reaction will be, whether energy will be stored, absorbed, or released. The thermochemistry, how the path of the reaction occur with the chemical kinetics property solutions such as boiling, melting points, vapor pressure, osmotic pressure can be predicted, compared, and measured values. Periodic chart of the table, also the number of individual naturally occurring elements is 92. Combination of metals, non-metals, however the number of the compounds, both natural as well as man-made synthesized, runs over 30 million. Many of the other polymers, compounds, metallic, ionic, covalent, and bonding characteristics, combination of all three. There are 4 states of matter: gas, liquid, solid, and solution. Mixture of the homogeneous solutions, whether one or more phases of the pairing with a heterogeneous for the 2 or more phases of the present collides. Colloidal dispersion intermediate with the state with a homogeneous heterogeneous mixtures. Specific examples include milk, blood, mayonnaise, butter. They do not separate upon standing, exhibit a Tyndall effect with the aerolysis emulsion foams of a general example of suspensions such as paints, other cough medicines which need to be shaken and stirred before use of the subcategories colloids. Chemistry is also helpful in examining chemistry, composition, solution mixtures, also helping elucidate subject matter by correlating molecular structure microscale with observation properties macroscopic scale, analytical technique. In modern instruments such as atomic absorption spectroscope and uncoupled plasma spectroscope, gas chromatographic with detectors such as mass spectroscoping, inflamed induced ionization, can identify elements, compound, solution, as well as quantity of the amount, some of the low parts of the trillions. And it shows a graph of part C, practice problems. Chapter 4, Computer Terminology, Spreadsheets, and Generic Programming.